Chris is a professor at Carnegie Mellon, where he's been part of the Robotics Institute since about 2000. He's also, very importantly, visiting faculty at this Robotics and AI Institute place in Cambridge. Chris started his academic career as an undergraduate down the street at Harvard, went to MIT for grad school, where he received his PhD in brain and cognitive science in 1986. Did you go to your graduation?
I did. It was wonderful.
It was?
Yeah.
It was cold and rainy.
Yeah. So
That happens to be the same year I graduated as an undergrad, and I have a rather horrid memory of having to sit on the Killian Court in the pouring rain when it was like 45 degrees. Prior to Carnegie Mellon, Chris was faculty at Georgia Tech. He's renowned for helping inspire Baymax. I would describe him as an expert juggler and magician. I think we'll have some demonstrations today. He also is a master bullwhip cracker. I don't know what the right phrase is.
that's good enough.
Bullwhip operator. But I have a distinct memory of an ICRA conference where Chris and I were slated to talk in the same session, which I think was like one of the very last sessions of the conference. This was in Atlanta, and Chris decided to drum up an audience by taking his bullwhip out into the hallway in the conference center and demonstrating to draw attention. I understand the bullwhip did not make it up as part of today's demonstration, so we're probably all safe. Enjoy. Thank you, Chris, for being here.
Thank you very much. Okay, today I want to talk about sort of my view of sort of where we're at, where we're not at with robot learning. And as was mentioned before, I have a degree in psychology, so I can talk to you about your feelings. And that sort of biases me to ask the question, how do humans do it? I see a couple challenges. Currently, teleoperation is a very popular way to generate training data for robots. Well, suppose you're doing a task that's very hard to teleoperate. We are spending a lot of computational effort and potentially time to train robots in simulation. And the question, you can ask the question, well, suppose the task dynamics change. Do you have to start all over again? So that's a challenge. And I've built my career on model-based everything. And now I'm going to flip ideologies and say, oh, accurate models are very expensive. Data from real robots is very expensive. How do we be as data efficient as possible, use as little training data as possible? Okay, I thought a real life example would be useful. So last week I was planting some trees, and the guy is delivering the trees, just dumped them in the holes. And the challenge was, how do I get the tree pointing up? And you would think, oh, that's easy, but they have root balls, and you can't just grab the tree and use it as a lever because you'll destroy the roots. The root balls are unbelievably heavy. I have no idea how heavy, but very heavy. And they're fragile. Every time you touch them, dirt comes off, roots get exposed, the tree whines at you. It's very sad. I first thought, well, let's use a lever. Top right corner, you see the result of trying to use I think it's a 2x3 rather than 2x4, but it broke before the root ball moved. And then I sort of harnessed myself up like a mule and, tried to brute force it. And then I asked ChatGPT how to do it. And this is how the world has changed. To be honest, a lot of things I'm going to tell you now, we knew decades ago, but it always required in the end a smart human to program the strategy for the robot. and we couldn't answer the question, can we get rid of the smart human? It appears that we can now get rid of the smart human and, use what I would call real intelligence, high-level thinking, to come up with strategies, and robots actually learn better ways to do things rather than sort of perfecting a bad strategy or the second best way to do things. Okay. So to explore these issues, I'm going to look at two case studies of dynamic tasks. One is pen spinning, and the other is something called flying knots. This is Krishna Suresh, who actually spent some time here, I think about 6 months ago. And the first and third are real time, and the second and fourth are slowed down, and we'll spend more time on that at the second half of the talk. And here is the ideology. As I say, I'm in touch with your feelings. I think human learning is good because we learn tricks, not because we, sort of build huge databases or average a lot of training data. Yeah, we use terms like, do you get it? And often someone will say, okay, what's the trick? When I do some juggling thing, what's the secret? What's the hack? We have words for these sort of, verbally expressed high-level strategies. And to me, that's real learning. I want to have a conversation with a robot at the level of sort of high-level physics. A huge win for human learning is dimensionality reduction. And I believe they achieved dimensionality reduction by using what I call parameterized primitives. A human, us, we know how to do things. We have a small number of parameters to adjust to adapt it to the particular task we're trying to do. And if you have a small numbers of parameters to adjust, you don't need a lot of training data. So that's a huge win in terms of speeding up learning. And we are trying to replace the smart human with instructional material on the web, chatbots, LLMs, whatever. And, I see the main challenge for robot learning is to push it up from, what is essentially low-level numeric learning to at least some level of reasoning and high-level strategizing. And I will be really impressed when robots, find better ways to do things and find ways to cheat. I often start classes by telling my students, cheating is very important. That's our real goal. We're going to start with a case study of pen spinning. I realize this is like talking to you. Over the years, there's been a gap between me and my students. It's like talking about inscribing stuff in mud tablets and waiting for them to dry and passing them around. So this is a pen. It is an archaic writing instrument. Most of you probably don't know how to write. Yeah, okay. This is a pen, and you spin it. And this is what a simple trick looks like. It's called a thumb around, and you essentially roll the pen on your thumb. And I just want to point out, because it'll come up later, that when a human does this, the pen rolls on the thumb. It doesn't lose contact with the thumb. And you can do this trick sort of with any orientation with respect to gravity. So we are not relying on gravity to maintain thumb-pen contact. And unfortunately, there was a group at the University of Tokyo who basically did all the cool stuff 20 years ago. And, we're in robotics, we're challenged by the vision folks who are invading our field and saying, oh, okay, we'll get robots to do amazing things. This is yet another example of a vision guy coming in and doing amazing robotics. The issue for them was they built a high-speed camera that took frames every millisecond or every 2 milliseconds, and they wanted to show it off. So they had to build high-speed robots that would move fast enough that they needed their high-speed camera. The rest of us had very slow robots, and we could live with slow cameras. Okay, so this is their version of pen spinning. And it's very fast. This is slow motion. If you look very carefully, the pen lifts off the thumb. It's actually throwing or bouncing the pen from one side to the other. And that's a little clearer. This is a student of Ishikawa who they inherit labs, so he inherited the lab. And here's a version of his pen spinning. You can see it's just flying through the air. So, okay, that's traditional robotics. And you could ask the question, what is traditional robotics, since current machine learning dumps on it all the time? And sort of my definition is some human sits down, comes up with a simplified or idealized version of the task, thinks it through and figures out, well, what do I have to control to stabilize whatever pattern I'm trying to do? And I would argue a classic example of traditional robotics is the three-part control of Raybert Hopper's that I hope all of you are familiar with. They, in this task, used high-speed vision to show off their camera. They also used basically force-sensing resistors as tactile sensing. And they basically went through all the degrees of freedom and figured out, is it passively stable? And sort of spinning in the plane normal to the fingers is. Is it ignorable? And sort of yaw, what I call yaw body yaw rotation around the axis of the pen is ignorable. Every time two fingers touch it, you basically shut that down. And then everything else they needed some sort of control loop on, and the tactile sensing became very useful for that. Okay. Now, what has happened recently is basically there's an approach which I call big simulated data. And Eureka, a recent piece of work from Jason Ma and others, what they wanted to do, the point of their work was to automatically generate proxy reward functions. And it was not to make real robots do things. So I'm going to show you what they did. It's all in simulation. That's not a criticism, because that was all they needed to show off their proxy reward functions. But it's the typical picture, which everybody does. If you start with a picture of one thing doing the task, and then you zoom out, and there are 9 things doing a task, and then suddenly there are all kinds of hands doing other tasks. Unfortunately, this fades out very quickly because some of those hands are doing really weird stuff. Okay. A group followed up on this and said, we'd actually like real robots to do this task. And this is what they achieved. They can basically, this is a version of pen spinning where you just use your fingertips, and they can basically handle anything that was a cylinder of roughly that diameter. For comparison, this is what a human looks like when they do it. And now I got to figure out how to advance the slide out of that. So they were very public about lessons they learned, one of which is, and I don't know what that is, but we're going to have to deal with it if it keeps going on. Okay, they said sim to real doesn't work very well for these kinds of tasks. And they said, it's very difficult to teleoperate these tasks, all of which makes sense. And a group with a soft hand said, well, we could do pen spinning too and rely on the natural dynamics of the hand. And we're going to sit through this video, even though it's very slow. because I'm making the point. It's very slow. So this is where I turn to every audience, say, are there any questions?
Yeah, I have a question. This is Howie.
Yeah, Howie.
How would you go about teaching somebody to do the pen spinning thing, like when they start, say, in their 50s? They didn't start as a little kid. And this
It's
is me
not too
asking you as
late,
a
Howie.
yeah, this is me asking you as a psychiatrist, not as a roboticist. For a friend.
Yeah. Just like people our age rely on 12-year-olds to make our remote controls work and our computer networks work at home, I urge you to get together with a 12-year-old and
Uh,
have them coach you through it.
okay, thank you.
Okay. So we also used a soft hand. I don't have a very good answer as to why we did that. It was basically because it was right in front of us in the lab. And it also was nice and smooth and round. Most robot hands, the fingers aren't actually round. And I needed a round finger to have the pen roll on it. This made the task harder because we didn't have any good models of the hand, and the students complained it's very hard to simulate, and it's not that fast. And this is the work of Yunqiao Yao and Jeff Ichnowski and others. And he did a great job on the launch and rolling around the finger. In retrospect, as I put together these slides, I realized we should have used the launch finger to come back and make a complete grasp at the end of it so it doesn't sort of rotate up and down. So I'm going to make him do his thesis over again. Okay. So what did we learn? Well, here's the deal. Every year we get new students, and every year I sit down and I'm sort of like an old Eskimo. Here's how we hunt the seal. And we got to start by building a kayak out of, old skins and stuff. And then we got to practice throwing the spear. And they say, I don't want to spend the time to learn all that stuff. I just want to collect training data and train something to do it. I don't need to take a class. I don't need to know anything. I just need the training data. And this student was just like every other student and tried that out. And because we had the Eureka work, which showed you could do it in simulation, he tried that approach and, came away from it. For him, it just didn't work to get it to transfer to the robot. And at that point, we asked the question, is there some other way to do this? And a subtext here is we're going to reject model-based control. So I'm a little late for a midlife crisis, but let's attribute that to a midlife crisis. In addition, this is fast enough and regular cameras are slow enough. I've never gotten anyone that has better than end-to-end of a roughly 45 millisecond latency. So we decided we're just not going to use feedback. And there are a couple of reasons for that. And I think the most important is, unless you have incredibly good measurements, feedback injects high frequency noise into your actions. Yeah.
Well, forget measurements. One of the remarkable things with this task is you wouldn't even have the control authority, even if you had perfect measurements, to stabilize something like this with.
Well, the Ishikawa folks argued that they did. Now, a big difference between us and the Ishikawa folks is we just did one rotation and stopped.
But I mean, a human being, I understand the Ishikawa guys. I mean, to me, that was the interesting thing about them is they basically could just close the loop.
Right.
But that's not really classically part of the task, is it? Right? Your human being isn't. I don't believe you're exerting any control authority.
The video he showed where the person was kind of juggling it continuously on their fingertips, like That's got to involve closed loop.
Yeah.
Okay, there are two control problems you gotta solve. One is, as you do this, the pen sort of walks this way and walks this way along your fingers. And you gotta keep it centered. And I do believe humans do that. Whether that means that they are doing a millisecond by millisecond measurement, adopt the action, that isn't necessarily implied. And the classic example is bumblebees that flap their wings at some outrageous high frequency. And they can steer and they can hover and they're amazing flyers. And they're clearly not controlling each wing beat. And, you know, the theory is if they sort of tighten a muscle a little bit, they'll go to the left and so on. So they have very low frequency parametric control of an oscillator that gets them what they want. And that's very different from sort of tick by tick control of the system.
Do you call choosing a mechanical configuration that has a local stability in it, a passive stability in it, control?
Absolutely. And, you know, in nature, you see a lot of, that's the system you start with, and then you use parametric control to steer it. I'm totally in favor of that. Okay, so if you look at instructional videos of how to do this, they are flat out saying, here are the primitives. The first primitive is grasp. The second primitive is launch. And they'll show you that with a pen. And the third primitive is catch with that finger. So we don't have to rely on smart humans to come up with the primitives. They're just sitting there on the web. We just have to figure out how to harvest them. So I'm very keen on that.
Wait. They only got on the web because some smart human defined them.
Okay. This is a digression. I don't think humans are all that smart. Most humans, yeah, you could sort of fix a toilet when it's running continuously or something like that. But they aren't Einsteins. They don't invent whole new ways of doing things. And I believe that if we look at the behavior of humans and you ask them at each stage, you know, did you invent that? They'll say, no. Where did it come from? You know, somebody showed it to me or taught me or told me. And the example I like to give is, you know, opening a jar that's stuck. You can't do it. What do you do? And people say, oh, I put it under hot water, or I whack on it, or I drill a hole in it, or I smash the glass, all of which are strategies that if you ask them, did you invent it? They say, no, you know, somebody showed me how to do that, except maybe the smash the glass one. The classic example that people like to talk about is the Fosbury flop, where, you know, in high jumping, everybody jumped over the bar belly down. Fosbury was a total pain in the ass. You know, his coach, he came out there, he said, I'm going to go upside down. His coach said, absolutely not. You're off the team. Had a lot of struggles, but he was sufficiently stubborn and ornery enough that he just persisted. Now, he didn't actually break any world records, but other people watched him do it, said, I get it. I understand the trick. You can actually have your center of mass above the below the bar as you go over in that configuration. And they adopted it and started breaking world records. And that's the kind of robot learning I want. I want stubborn, ornery robots that refuse to listen to me. Now, I sort of have that now, except they're not that smart. Okay. Once you figure out here are the parameters, you then have to figure out, here are the primitives. You have to figure out, okay, what are the parameters? And, for graphs, it's sort of obvious. Where do you grab the pen? For the launch, if you're starting out in the grass configuration, it's sort of where do you go to? And the student picked an arbitrary movement duration. You could have varied speed. That sort of trades off. You could trade off the target pose versus the desired speed to control how much energy you put into the pen. And the catch is very straightforward. You just close your hand. All right. We used a technique called evolutionary optimization. I don't think it matters what technique you use. This is about, in your mind, the different strategies have group sex, produce children, and then you kill off the bad strategies. And each generation had 13 people in it, or strategies. CMAS is really weird. The maximum population you ever need is 16, no matter how dimensional the problem is. And it took about 10 generations to get 100% success rate on most everything. And, that's not a lot. And what it enabled was, if I give you a pen with a different mass distribution or even a different object, you just start learning over again. You don't need to generate a robust policy that can handle a wide range of objects if you have sufficient data efficiency to just start learning over again when you have a change in task dynamics. And that is super important. Right now, when people do what I call big simulation data approaches, they are relying on there isn't enough task variation to cause this policy to become invalid. Because if there is, I got to start all over again. Where does this power come from? It comes from, we've turned the learning problem into selecting a bunch of primitives, which you basically do once, and then twiddling, parameters for each of the primitives. And given that we were using a non-anthropomorphic hand, we couldn't copy people, so it wasn't important to match exact trajectories or contact points or even the details of the object motion. Now, what did we not do, which makes it future work, is we just did one trick. There are a huge number of pen spinning variations, and it would be great to explore how do you efficiently learn all these variations. That actually is an issue that has been addressed in quadruped parkour, and in fact, hopefully some of the people listening to this will be saying, yeah, I solved that problem already. Okay, that's pen spinning. That was the first case. Now we're going to do trick roping. And again, it's a fast task. The variation we're going to do is something called flying knots. And I'm going to introduce that, showing you a video that was made a little over 100 years ago. Here it is. The cowboy is Will Rogers. That is an overhand knot. He just wiggles the rope. It comes up with a knot. And I'm going to just let this run. That guy, this is a movie. It's shown in movie theaters. That guy is the heckler. And his role is to say rude things interspersed with these demonstrations of roping. And the whole movie is about, an excuse to show roping tricks. Now, let me give you some historical context. That's the heckler again. Will Rogers was the Jon Stewart of his time. He is famous for his political commentary, which he would give, while jumping through a hoop. Okay. I also need to explain to you that before we had video games and smartphones, and I see some of you are playing with your smartphones right now, people had nothing to do. And there was genuine interest in these kinds of skills. Anyone could do them. And this guy was one of the most famous people of his time for doing these skills. And, you know, the sad thing is nobody cares anymore. They're just playing with their video games or smartphones. The monkey, I'm not sure what the meaning of the monkey is. You know, maybe it's to say, you know, anyone can do this. He actually, it looks like he did a flying knot there. Okay, so once again, the Ishikawa people scooped us. Okay, so the way you do this is you find a human that can do the trick, you video them. They didn't actually motion capture the guy, they just use this for inspiration. But here's his, and by the way, these are all slight variations of the same strategy. This guy's going sideways, we go up and down. I love this video. Here it goes. That's it. That's the video. How the hell did it work? Okay. So if you read the paper, they used a very crude rope model. Essentially, they said the rope just follows wherever the hand goes, which is not true. They unknowingly made the robot task harder by using a string-like thing instead of a nice thick rope. And that's much harder. And their human wasn't very good, only got about 15%, and the robot was a little bit better with 20% success rate. A very interesting research issue that I'm sort of bordering on is, again, how do we make tasks easier so we can up the success rate from 15 or 20 to 100? And okay, I'll talk more about that later. So this is Krishna Suresh. First is normal speed, slow-mo, normal speed for the robot, slow-mo. Now, the robot didn't learn to do this task. The human learned to program the robot to do this task. We are still working on the robot autonomously learning to do this task. I think it's very interesting to measure Krishna's performance as if he was a robot. In human learning, we typically break it up into several phases. The first is a cognitive phase where you figure out, what am I doing? And roughly it took him 40 to 50 trials until his first success. Now he knows what he's doing. And the second phase is called an associate phase. And people usually say something that's sort of voodoo, which is you stop consciously thinking about the task. You're sitting there, you're practicing, and you're thinking about your email or something. And that took about 10 to 15 trials, got him up to a 50% success rate. And then people talk about the expert phase, and you know, there's this meme that if you do something 10,000 times, you're an expert. That's what they're talking about. He actually didn't do the requisite 10,000 times. He only spent about what he says is 5 to 6 hours over a month, random time, grab the rope, do it. That got him up to 80%. And then he slacked off. He didn't practice every day. And now he's down to roughly 35%. That's human learning. Now, human learning to get the robot to do the task, it took him, we use something called an X arm. It took him 2 days to get it to move fast and smoothly. When he started out, the table shake, everything shakes. And he couldn't do anything. Once he achieved that, it took 40 trials, only 40 trials, for him to get the robot to do it, to the first success. And with robots, you know, once you get the first success, you're golden. You just keep playing the same thing over again. And that day, you know, he was up to 85%. He was totally happy. The next day, performance is totally gone. It's down to 20%. I have, you know, it's a robot. It's supposed to do the same thing every time. I have no answer to the question, why is that happening? We can generate training data. He got in front of a mocap system and spent an hour generating training data. That's nice. And then we said, okay, now we have to do the real work, get a simulation going, show us autonomous learning, da 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 da. It has taken him months to get a simulation where, and it's still not accurate. It's still not, you'll look at it, you say, well, it looks like spaghetti, not a rope. But here goes. Again, what are the parameters? I asked him, what were you doing when you were programming the robot? He said, well, there are 3 points. You start, you go up, you go down. And he used human intuition to figure out what good values for those points were. And then after that, he sort of varied a few joints, not all the joints, to vary those points. Okay, so now I'm going to tell you about the simulation part. So we mocapped him, and that, I'm going to argue that the trick of the trick is that posture of getting the rope into that configuration. And so here is the system learning to do that. That's the reference trajectory. This is 2 ropes. After learning, they match pretty well. And then I'm going to show you all the trials. Again, in simulation, 1, 2, 3, 4, 5, 6. Holy moly. And we're done. And we say, okay, that's good enough. So that's the kind of data efficiency I'm looking for. And okay, I always have this problem if I have multiple videos, I can't turn the page. Now let's do it in 3D. Again, okay, that was supposed to be mocap. This is the spaghetti, and that's the spaghetti succeeding. And 1, 2, 3, 4, and we're done. Okay. What this is learning is to imitate the mocap trajectory. And you hope that that results in them not being tied. A much better approach, which we do not yet have, is something that understands that you got to form a loop. And I'll talk about you hit the rope with another part of the rope that flips the end into the loop. And what do you want to learn? You want to make the loop as wide as possible. And you want the end that's flipped to go through the middle of it. And that would be real learning. We haven't gotten there yet. Okay. Okay, how do we learn so fast? And the answer is something that I'm going to call feed-forward command learning. We learn a feed-forward command as a function of time. We're not saying you have to be open loop. It's fine if you have an existing controller. We're just not changing it. In this case, we are open loop. Okay, why is that a good idea? Because you're trying to learn something that, basically the comparison between a policy and a trajectory that's refined is the difference between how many steps you have in the trajectory versus how big is your state space. And that is a huge difference. And I'm not telling you how to handle disturbances. We don't have I'm not learning feedback. If I already have it, great. If I don't have it, bad. That means I can't use this to control unstable systems. And this is, you will see it's reliant on models. It doesn't actually, it handles modeling error, but it doesn't make the model any better. And this is actually work I did 40 years ago in my thesis, at least the start of this. And the deal is very simple. The first half of my thesis, which Mark was on the committee for, by the way, so for him, this old hat, we identified, yeah, I don't remember it either. Basically, we were trying to figure out how much does the robot weigh? What are the inertial parameters? And we were doing that by waving it around. Okay. And we were really proud of our model. And, wow, what a super model, 1% error or something like that. And we need to make the cover for this book. And it's a little hard to see, but we stole a technique from the leg lab. They put LEDs on their hoppers and generated these, turned the lights out and took a long duration photograph. And you saw a red LED going hop, hop, hop. Okay. Maybe this is too personal, but I asked Jessica, let's do that with our robot and let's get it to sign my name with the red LED. And we tried that. And it's like, famous president's signature. It looks like garbage. So then I had a serious problem because, what good is it to make a model if you can't use it to control well? So the recovery was, let's have a desired trajectory, and the upper left here shows you the commands. And if you run those commands, the lower left shows you the velocity errors. And then I'm going to do some magic trick, and 3 trials later, the modified commands look like the upper right, and the velocity errors are greatly reduced. Okay, so what's the trick? Well, we want to map trajectory errors into feed-forward command corrections. I didn't invent this idea. There's a Japanese guy named Eramoto. And, he said, well, he proposed some learning operator that took the errors and mapped them to corrections to commands. And he called it learning control in 1984, which was a little over aggressive because, it sort of said there's no other form of learning. And over the years, we have struggled as to what to name this thing. Other people have called it repetitive control. Other people have called it iterative control or iterative learning control. There's another version called feedback error learning. I've decided to invent an all new name last night as I made this slide. I'm going to call it feed-forward command learning. Yeah, okay. My version is very simple. If you take the command and you pump it through the system and you get a trajectory, then on the right-hand side, you have something that is in units of trajectory. It's an error. You want to pump it backwards and generate with a change in the command. And I look at these 2 pictures and I say, well, the learning operator, the lower thing, should just be the inverse of the system, which makes it an inverse model. And so there's something that roughly looks like equations. The top thing is the system operates on the actual command. We compare that with, some predicted command that gives us an error in commands. And because we're running it through the system, has something to do with the error in trajectories. And to run that backwards, we just apply the inverse model. And so the correction to the command is the inverse model applied to the actual trajectory minus the inverse model applied to the desired trajectory. Very simple. This will converge as long as your model errors are not too bad. And there's a philosophical statement it generates, which says, if you want to learn efficiently, you should already have a good model. Okay. That's how I left it 40 years ago. I did not answer some obvious questions, which is, suppose an inverse doesn't exist because the mapping in one direction is one to many or many to one or whatever causes problems. If the mapping the other way is many to one, one to many, inverse doesn't exist. The other thing is, if you have modeling error, that actually gets pumped into the system. A third issue is high frequency noise that is pumped into the system by your feedback controller this often you have very bad models at high frequencies. So this actually often amplifies high frequency noise. So it's really good. It's data efficient because you shut it down after 5 trials anyway. Okay. So 40 years later, a student working on this is generating something called optimization-based feed-forward command correction. And the idea is, again, very simple. We're going to predict the effect of a correction, and we're going to regularize the correction by trading off how big the correction is and how the benefit that we predict. So we predict the error, get a norm, we have a norm on the correction, we have some weight to trade those two things off, and that tells us the best correction to apply. And that was what was doing the learning and simulation there. An obvious question that we haven't addressed yet is, if we're doing all these trials, shouldn't we be making the model better simultaneously? And the answer is obviously yes. Okay, so we have the machinery to be very data efficient if we basically have already formulated the nature of the solution. And the real point of this talk is we can harvest that off the web. Okay, so there are many videos on how to do these flying knots. Here is the transcript of one of them. And the research challenge for us is to take this kind of verbal stuff and turn it into something a robot can understand. And the key element of the statement is, take this piece of rope right here in front of your finger and trip the Honda right above it and make it flop over into the loop. And we need to turn that into something a robot understands. The Honda, by the way, is, that's a Honda. It effectively is a weight on the end of the thing. Another thing we learned from this narration is you can make the trick easier by having a bigger weight, which was very handy information. Okay, so while they're giving you this information, they're also showing you, okay, let's go.
Then we make a circle with our finger, which will make a
So
circle in the
he's
loop.
giving you desired
Tap-
trajectory.
Tap that rope right above the
Uh,
Honda.
Sorry,
Or right beneath
I
it,
forgot
wherever
there's
Honda's
audio
at.
here. Okay. And then he shows you in slow motion, and it's the contact between the two ropes is the key point here. And then in the video, he shows you another view, and that's the contact between the two things here. And if you look at somebody else's video, very similar. Now, he actually hit it with his finger. And when I learned this trick, that was the trick of the trick. You have your finger extended along the rope, and you're mentally whacking the other part of the rope with your finger. And that makes it super easy. That for magicians are never supposed to tell you how they do their tricks. Trick roping, probably very similar. So, I've been doing this for years. I've never told anyone. Now I'm telling you, you'll probably have to kill me after this. The secret is put your finger along the rope and just push it down and effectively whack the rope with your finger. That alone.
Then we make a circle
Yeah, I got it.
with our finger, which will make a circle in the loop, and tap.
Okay. So I'm going to end here and say, I think we have a tremendous opportunity to harvest the tricks of the tricks off the web. I think I can see how to do it for non-dynamic tasks like assembling furniture. It's very clear how to do it, and you use diagram understanding, and VLMs and stuff like that. For dynamic tasks, there's not a lot of information about forces on the web, but I still think we can do it. And the idea that we basically do it by having a library of parameterized primitives gives us huge dimensionality reduction. Now I'd like to have an argument. You guys, including the people in Switzerland, have had great success doing big simulated data approaches, where you do a ton of simulation and you turn that into policies, and then you do sim to real. I'm advocating something very, very different. One issue is how do we reconcile these two things, because they both work very well. Another issue is, how do we take advantage of traditional robotics? For both of the tasks I showed you, the Ishikawa folks just sat down, cranked out a controller, and quite frankly, they have the best performance of anybody. And my answer to that question is, we get a lot of those people together, like we have here, and we just sit down and we crank out all the primitives we need. And then we're done. We only have to do that once. And now we have a library of great primitives. And now I'm going to say something else, which is controversial at CMU. I think learning to do a particular primitive is a solved problem. It's an argument I have with Deepak Pathak. He thinks learning to do a particular primitive is the problem. And all the stuff I'm talking about, which is what primitives you select and what parameters, yeah, fine. That's easy. So there's an argument there. Okay. So I'd like for you to sort of your comments, but there's one last thing I have to say, and that is a word of warning. To me, I sound a lot like the folks that said we should study human cognition to make good computer chess players. Okay. Comments, questions, thoughts?
Seems like there's a lot of knowledge on the internet, of course, but right now it's represented using language. And I've always been a little skeptical that English is the correct intermediate for representing physical actions because it presupposes a strong prior in the physical world. Do you have any thoughts about how we might try to bridge the strong language prior and the physical prior we need?
Okay, from my point of view, you're looking at this glass and saying it's half empty, that language is limited. I'm going to look at this glass and say it's half full. Language was invented so we could explain how to do these things to other people, our children, whatever. So if you ask me, what's the best way to get a list of primitives that we need to implement? My answer is open a dictionary and take all the verbs that involve physical stuff and implement those.
I think David's point is something like, without an appeal to subatomic particles, we can't explain in language the difference between left and right. And the question is there a whole range of aspects of the physical world that are not captured by language?
Clearly, but they also don't matter. This left-right distinction, I never got it straight. No, I'm going to give you the classic answer to that question, which you may or may not like, which is we have struggled to define what pornography is. And, in the legal field, the best answer is no, we don't have a legal definition of pornography, but I know it when I see it. And this is the grounding problem. And I think we've made tremendous progress on the grounding problem. We can train an object recognizer to recognize what a chair is. When I was a graduate student, we would tie ourselves in knots of arguing what is a chair. And that problem is, from my point of view, solved. Laura?
So when you did the pen spinning, you made a statement where you said, it's so data efficient if we have the right parameterized skills that we don't need to keep any information that we learned about some previous pen trick, for example, right? As long as you have the good primitives, you can learn on the fly what the parameters are to this particular skill. And what I wanted to ask was, how much do you think there is some underlying knowledge that humans, or in this case, robots, have to have about how to achieve those tasks themselves, like each of the parameterized skills? There must be some fundamental information about that the relationship between this particular goal and how to reach it that is common across many different pen tricks. And it seems to me what you're advocating for is kind of throw that away, just learn it on the fly. Is that the right interpretation?
Not, okay. Let's distinguish between what we do at execution time or learning time and what we've already done. What we've already done is build the internet and all that knowledge. What I'm doing at learning time is trying to extract some of it. Now, what stopped us from doing this 30 years ago? I could have given this talk 30 years ago, except I didn't have all the internet stuff. So I didn't have an answer to the question, where's it going to come from? Now I have an answer to where's it going to come from. And I'm waving my hands on, if you have an immense mountain of this stuff, how do you get just the right thing? And generalization across tasks, again, 30 years ago, we talked about activating nodes in a network that sort of said, use these guys because you recently used them, that kind of stuff. That's probably what generalizing across tasks looked like. If these primitives work well for this pen spinning trick, then they'll probably work well for a similar trick.
How many primitives do we need? Sorry.
As many as there are words in the dictionary, roughly. So 30,000.
Question for you, I think it's around 5:45, but how do you define for the knot throwing task, how would you define that the knot is successfully done when you're in simulation and learning tasks? Because I can imagine you doing a discriminative classifier, as you pointed out, it could be remarkably robust, or do you actually have it like compute the trajectory and check that it's like not from knot theory? Or how do you do it?
We do it in the crudest way possible. The rope no longer looks like a straight line.
Code in your simulation? How does the computer know?
Okay, right now, we have not explored that in any serious way.
So it's the Potter Stewart answer. You know it when you see it.
Got it.
Yes.
So he's built a classifier.
No, we're gonna use big data. We're gonna train something to recognize success.
If you accidentally tied a slip knot, it would give you a false.
Well, that's what I was
positive.
teasing at, right?
Yeah,
Exactly.
yeah. And for a human learner, they hold it up and say, wow, cool, look what I did. And if the robot did that, what I'd want the robot to say is, wow, I've learned a new trick.
Thank you.
So you made a compelling case that learning methods should be applied at a high level to these parametric problems, but something still has to occupy the low level, high frequency space. And my question is, that low level, high frequency controller is still model based. Have you really succeeded in creating a system that's capable of learning new dynamics? Or how do you put something in the low level control slot that allows you to take advantage of the flexibility of the high level parametrics?
So I'm going to admit something. I have for a long time advocated using optimal control to generate both desired trajectories and controllers in a sort of a tube around that trajectory. So you have like PD servos running all the time and they can vary along the trajectory. The PD servo gains we get out of optimal control are usually way too aggressive and don't work. So we replace them with default gains that we know, because we've done a lot of different stuff, work over a wide range of things. So the honest answer to how do we generate the feedback component of control is, well, we basically have some very strong priors, which we reuse over and over again. And when we get a robot to do different tasks, we are only varying the feed forward command. So in your context, for example, there's the wonderful work with eAtlas where it does handstands and backflips and whatever. I bet that if you looked at that carefully, the feedback component of those things is all roughly the same. And what is varying is the feed forward command along those trajectories. I bet that you could apply the approach I put forward here to get eAtlas to do those tricks. And as long as you used feedback controllers, the same gains throughout the entire thing and across all tasks, I bet it would work just fine. Yeah.
It's probably true even for humans. When they start out learning, they use a lot of feedback. But once they become experts, it's mostly feed forward.
Yes, except for tasks where you absolutely must use feedback, like balance, controlling an unstable system. You got to have feedback. There are minimum gains, otherwise you're going to fall over. What is usually said about expert versus beginner control is the beginner is putting together a lot of primitives, and the expert is consolidating that into one big primitive. And, is that true? I don't know. We'd have to open somebody's brain to figure it out. And it's going to be a long time before we can do that. But, does it seem right? Yes. Other questions? Yeah.
So one of the diffusion policy demos that I found most compelling in the original paper was when they were saucing a pizza,
Yes.
just because that's something that I don't know how to simulate or even describe the state of. Do you see these sort of like primitives and ILC kind of approaches being able to, like, how do you take if the robot throws the sauce against the wall, or if the robot, only half sauces the pizza? Like, do you see a way forward to being able to like improve on that task?
This is the TRI stuff,
Yeah,
the pizza.
the original, diffusion policy.
Okay, I have a former student on that team, so I have to be very careful what I say. I don't think they have any idea where the sauce is. I mean, or maybe they do, but they're driving a compliant ladle. They don't really have to worry about vertical because it's a compliant label. They just have to worry about coverage. I retract the statement, they don't know where the sauce is. That's probably not true. But I don't think it's that hard to do that pizza task. That's not to say that anything they haven't done is not hard. It's just to say, I don't think the pizza task is hard.
I mean, yeah, I agree with you. If like you could probably do an open loop or something like this with a compliant control. But I think bigger picture for systems where in a simulation it's really hard to describe the state, or like to understand like what an improvement direction is. Like, is that kind of where these ILC kind of approaches would struggle?
I don't think so. We've turned it from you're trying to hit an exact template to solve an optimization problem. The optimization criteria can be anything you want. One of the things I'm interested in doing is getting some of the robots around here, which are really fast, to crack a whip. What's the feedback for cracking a whip? It's a sound. The sound doesn't give you any information about forces or trajectories or anything. Do humans learn to crack a whip by just listening to it? Absolutely. So, can we do that? Yeah, sure.
So you're saying the reward can capture a lot of this, basically.
Yes. And whenever we have a problem, we're going to use that deep learning stuff. Okay. Well, thank you very much. I brought some ropes if anyone wants to try anything.
I wonder what percentage of pizza sauce in the world is already applied by robots.
Yeah, I'm gonna kill somebody. Yeah, okay, that's it. Quit while you're ahead. Let me turn this off.
Yeah.
That's the first time